screen is not visible because of internet issues there from the co-host side. I don't have internet, so unable to make me co-host because of Chennai weather is all of
But are you also in the Chennai?
No, I'm not in Chennai, but host person is in Chennai.
In
Okay,
Chennai, there
now
is a
Yes, sir.
very
okay. So let me now I am co-host. Let me present my screen. Okay, so let's start the session. So in graph theory,
uh,
yes.
So please give the summary of each thing.
So let me start. In graph theory, we'll know about what is the like how the graph theory is started. Like the why the best example is talking about the this circuit of train that path connecting to two stations. So that is a like it is a virtually we can not virtually like we can see directly that they are connecting to two trains, and that is suppose the node point is stations. Those are the node point, or even simply in other ways the airports.
yes,
And connecting flights are like suppose this is Chennai, this is Mumbai, and this is Delhi. So connecting flight is like sure able to travel from if you want to travel Mumbai, so you have to go first Chennai and then Mumbai. So the routes are like the routes, whatever the routes are. So these are the cities, and the connecting flight, whatever the available flights are, like the whatever the routes to go Mumbai is like this. Like first you have to go Chennai from Delhi, then Delhi from sorry from Chennai to Delhi. So if this is the route, so this we can represent in whatever this is structure. This is structure is called this is structure. You may said this is a graph. Like this is a graph, and any more many problems like could be changed in real life problem. Simply there is in a hotel is there like the vertex cover is there, no minimum vertex
yes,
cover, and coloring the graph is there. So minimum vertex cover is that before to vertex minimum vertex cover there is that simply example is that suppose there are uh, these are the corridors, and this intersection point is the intersection point of the corridor. So these nodes are actually intersection point of the corridors. So suppose like these are the corridors, and then like this we can assume that these are on these sides are rooms are actually, and these are the corridors. An intersection point is or nodes are actually the intersection of corridors. So and you want to install camera, so how much like at which places need to install so that minimum number of camera could be installed. So this is one example of real life example of graph theory. So because of these situations, like graph theory have generated so many things are slowly have generated, like independent set is there, coloring, graph coloring. So graph coloring is came actually simply that you know deciding the boundary of states in I don't know that I am unable to draw the graph of India. That is very I don't know how it could be, but whatever the states are you want to suppose states are
Okay.
meeting at one point, so we can represent that three state and this boundary point is actually meeting at single point. So how we can represent this three state? We cannot give same color. We have to give different colors. So like this, if we'll start color the region, so what would be the minimum number of color is needed? So this could be change in graph theory problem that the nodes are actually what sorry so edges are, so this is called edge and this is called vertex. And that if two states are joining or or sharing the boundaries, okay, so we can represent this is that then these are the states, and if they are sharing the boundary, that means you are joining a line between these two states. So this problem could be changed in the graph theory problem, and then we can convert that, or we can think that how many colors is needed to or suffices to color the whole graph with the different color. And the constraints is that we cannot color two state with the same color if they are sharing the boundary. So like this we can think, and we can change the real life problem in the graph theory problem, and then we can do. So there are so many things like planar graph is there, and different use graph coloring, independent set, and minimum vertex cover. And there are we'll see the some algorithms are there that breadth first search, depth of first search, BFS, TFS, these all have. Okay, so slowly this is just a motivation to know that what is a graph or what we are going to study in the graph theory. So let me clearly specify that. So such kind of structure is actually graph. Okay, and this is called nodes or vertex, and these lines are actually called edges. Okay, and the graph could be directed graph also and undirected graph. Like this connecting flight is if it this airport connecting to airport. So the route, this is the route. So suppose I am just giving this direction and this is the direction. Suppose I just the graph is now a bit changed, and that I have provided or I have given the direction here. So if you want to go Delhi, so we cannot go only the outgoing edges. So this is called outgoing edges from Delhi. Okay, and this is for the same edge is going to be incoming edge for the city Chennai. So if you want to go Delhi, you cannot go because there is no route to go Delhi. Yeah, but if you want to go Chennai, so we can go to Chennai from there is one route that we can go from Delhi. So such if in the graph edges are as in the form of written as in sorry that in the form of that edge or a direction is given, so that such kind of graph is actually called directed graph. Otherwise, uh, undirected graph. So there are two types of graph: directed graph, undirected graph. So either the graph could be directed, or it could be undirected. Okay.
Yes, sir.
Sir, one question. If there is an incoming edge and outgoing edge, so the number of edges between these two vertices is 2 or 1?
In that situation, like we are not going to study the loop kind of thing. Like if it is like this, you are talking, no?
Yes. See, this
So
can be
if
represented just by a single line without any arrows, which means it's
without
an
any
edge.
arrows,
In
yes.
indirect graph, like so.
Yeah.
So we can think it such kind of situation for undirected graph.
Yes.
But yeah, these things are actually available. Like if you suppose only one direction now given like this, so this will come like it is saying to be okay. So we cannot, either it could be in a graph, it could be not like this. Only some edges are in the form of direction is given and some of not. So it could be either like this would be given, okay, and either could be there is no arrow.
Now,
So
for example, if you have 3 nodes, sir, okay, and in these 3 nodes, all edges doesn't have any arrows. They are connected one to one. So this means that from A to B and B to C exists.
yes,
So if I
yes,
have to
yes.
say how many edges are there here, is it the edges are 3 or it is 6?
No, no. So only 3 will be counted. It will not counted twice.
But actually,
will-
there are 2 edges, right? A to B and
So
B to
here
C.
for the directed graphs like this, so that's why for this ambiguous kind of thing, we'll try to avoid. So for this situation, for this kind of situation, we cannot think about it. So it will be like this. Okay, it would be like this. Like in both ways, you can go.
No,
And in
you have
this case, yes.
no. The question is very simple. In the
Mhm.
first 2 nodes, no, how many edges are there? Are there 2 edges or 1 edge?
If only 2 node is there and this is you are saying.
Yeah.
So
How
this
many
is
edges?
one edge, 2 vertices and one edge.
It's 1 edge, right?
Yes.
But the meaning is that the edge exists from A to B and B to C also, correct?
No, V to A. If
So
only two.
we will not say edge A to B and then again another edge B to A. So you mean to say these two are vertices are joined with an edge.
These
That's
two
all.
are connected.
Yeah,
But the
connected or
direction of
joined with
connection
an
can be
edge.
from
Yes.
both.
Yes. Yeah. Sorry.
The direction of connection can be from
Yeah.
both sides, right?
Yeah. In this case, the direction is going to be both side, but there is for such situation, this will come under the undirected graph. Okay. So that's why if it is each vertices
So
is like
in
you can
summary,
say
in summary, it's only one edge, correct?
only one edge. Yes. So the graph is only two type. Either it could be directed or it will be not or undirected. It will be not the mix up of directed and some of them as directed, some of the edges
No, we are not
directed.
talking about any mix here.
Mhm. So
So
in such
in
situation,
summary,
only
it is
one edge is
only
there.
one,
If
one edge.
only one edge is given, then in that situation, only one edge is there.
Okay, understood, clear.
So
Huh?
we have studied about connected graph. So is it possible that direct graph can also be connected? Means if there is a direct graph, then it cannot be possible we can reach everywhere from.
So so connected graph means if there is an edge, then we will say yeah, we cannot reach out to, yeah, this is one good thing that if it is like this is given.
And if there is a directed graph, then we cannot.
So we cannot say that these are the vertices we have A, B, C. So we cannot say from C we cannot reach to A, but we can reach to A from A to
C.
B and C. So from B or we can reach to C.
Yes.
So in this situation, like a graph could be connected or not. So in that situation, we'll generally talk about for undirected graph. Okay, if such ambiguous thing is there, if it is not clear, then we can come back to for undirected graph, and for undirected graph, it is connected, then there is an edge. Generally, we will say there is an edge. Otherwise, there is no mean to talk about for such that for such graph that is this connected or not.
Okay, sir.
So generally, then we can say for such situation, if we are talking about the connectedness, okay, then in that situation we will say undirected graph. We will study only for undirected graph.
Yes, because it's not possible that there is a connected graph or also
Yes.
direct.
Yes. In those situation, how it could be like defined? No, it will be
So
properly defined.
you
But
mean to say a directed
actually
graph cannot be a
categorize that,
connected
okay,
graph, is it?
directed graph and undirected.
Sorry, no. Do you mean to say that?
No, we cannot say in that case, and even we cannot going to talk about this. Such we cannot going to talk about like if how so if you see the definition, the connected graph is what is the connected graph? If from any vertex to any vertex you can reach out, but here from C you cannot reach to A, but from A to you can reach to C. So how you can now define is this a proper definition for connectedness? No, right? So then in that situation, we only talk about for undirected graph.
Yes.
Even the definition itself says that the meaning, no?
Yes, sir. We
So
cannot reach.
it's depend on that how the definition is defined, okay? And generally the connectedness is related to the undirected graph for undirected graph. Okay.
So we need to learn
Yes.
the way we need to learn method of DFS and BFS, how is going on.
Okay, we'll try to in this session we'll try to discuss at least BFS and DFS. With topological sorting we'll discuss later. Okay, but BFS and
Sir,
DFS in this
is this
session we'll try to cover.
graph theory is
Yes.
coming under topology? Yeah, I just have a general question.
Not topology.
Okay.
Topological sorting is there. Topological sorting, there is one dependency of, there is one different, not even different, directed graph would be, and which is acyclic. Acyclic means there is no cycle in that graph. Then what is we can do? We can sort out the vertices, and it is totally depend on logic that there is a dependency of the work. Like if a vertex is given and another vertex C is given and direction from A to C is given, so which work you will like A is represent a work and C is represent another work. So which work we will first do that. Without doing A, you cannot do C. So in this, for such kind of problem can be sought out or can be done by with the topological sorting. What order we will choose so that the work would be done within the within our very in a proper order, like doing the course, you are doing a course in suppose you are doing some courses. So one course, or suppose A B C D F G H are courses is there, and it's is given that without doing A course you cannot do D course. So dependencies are there. So which order you will choose so that you are able to complete the course D, and for D course, the course D is actually our prerequisite is there. There should be without doing, like for example MLF is there, so without doing this maths 1 and maths 2 you cannot do MLF. How it could be you can do?
Yes, sir.
So we'll see the topological sorting. While discussing topological sorting, we'll discuss there. And there is no, the topology is there, there is no meaning of it will come as a topology, in the MSc course.
Yes, sir. I was just curious.
Okay, so now this is just so these are the these nodes. This is called vertices or nodes are there. So these are generally called edges. So this is from for undirected graph. Generally there is no arrow, and for such graph we'll say undirected graph. If there is an arrow for each vertices, or sorry, for each edge is given, then that is called directed graph. And we'll see later. We'll discuss that for the directed graph. We'll first let's study about undirected graph. So there are different type of real life problem is there. That one we have already seen, the minimum vertex cover. So what is the minimum vertex cover? What is the vertex cover? First thing, okay. Before to study, like before to start discussing that, I will let me show you some videos are already available. I will suggest you that please go through with these live sessions. These live sessions are really helpful. Okay, Solvita sessions is already there, and open session, one open session is there, and one already Solvita session. So I think the Solvita session is in this for week 10 is not going to be deal because already it is available in the portal. But open session, these two sessions are actually will really helpful for all of you. Okay, so try to watch this also. In a quick way, you can see that with the particular problem, you can just jump on the YouTube and see how we can solve that or anything. Or want to go with the doubts, you can go with the open session. So let me go with some example. So with the example, we will see that what is the vertex or minimum vertex cover.
Excuse me, sir.
Yes.
Yeah, sir, in activity like 10.1, question number 3 is there. I am a little confused with that question, sir. Like, if you
Which
can.
activity?
10.1, sir. 10.1.
10.1. Okay. Which activity?
10.1, question number 3.
In this problem. Yeah, so this is one real life example to convert electric circuit problem. Here is this is a some electric circuit are there, and we want to convert this problem into graph theory problem. So see that how this is done. So this is a resistance is given and this is a wire. Okay, if two resistance are connected, with two resistance is connected, the wires are actually these wires are actually representing nodes and resistance representing what? Edges. So if you see that, okay, resistor is equivalent to two nodes. So resistors are actually
two nodes. That's what I'm confused here. Two nodes. Resistor is equivalent to two nodes.
So resistor is equivalent to two nodes are connected with one edge shown in the figure. Okay, if there is no resistor, then it will be counted as only one node. So if that means here, what is that? So here is the resistor can be represented as the edge of a graph. Resistor is equivalent to two nodes. Okay, so so yeah, that's the thing here. So here is resistor is representing what? If edge is given, then what it means that it is actually connecting to vertices.
Yes, sir. Vertices.
So if, for example, see that. So see that this is one edge, this corner, if you think these are the wires. So wires are actually representing what? Vertices. And resistor represent edge. So now see that this is one edge, this is one edge. Sorry. This is not, this is one vertex, this is another vertex. And these two vertices are connected with this edge, right? Now this is one edge. Now this whole thing you can think as a vertex. This whole thing is actually vertex. Now these two vertex, this one and this one is connected with one edge. Similarly, this vertex wire is actually edge and resistor is actually, sorry, wires is actually vertices and resistor is actually edge. Now these two, this is one vertex and this is another vertex connected with the edge. This could be, now here is changed. You can see that this is one, this and this is one. So yeah, it is actually not exactly in the same form. It is actually some rotation is there, but yeah, This is one. This is the way.
So the
Now here, if you
excuse me, sir. So this last part is like the
yes,
single
yes.
only one vertex is there. Last this whole gap, the wire
So
section.
this one, yes, yeah, this larger wire, see this wire, no, this big
Yeah,
wire
yeah,
is one
yeah.
vertex, is there? Yes.
Okay, okay, okay.
We can see it here also with the, let me draw it here. So we can see this is one vertex, this is one vertex, and this is one vertex. And this is connected by, see that? Right, this is one, or simply we can,
Okay.
this
Fine,
is
sir.
actually the same thing is there, right? Now the same way we can think this is one vertex, this is another vertex with this bigger one, this is one vertex. Okay. This whole is one vertex, this whole is one vertex. This whole is one vertex. This whole is one vertex. And these are the so we can convert this is one vertex, this is one, this is one. So these two are actually connected. Now this two also connected. There is another vertex. So this is connected. Now this is another vertex here, and which is connected by this and this. By this is going to be your graph. Okay. Now let's talk about the minimum. First, we'll see the graph coloring. But before that, let's talk about the minimum vertex cover. So what is the minimum vertex cover? First, what is the vertex cover means? Suppose this is these are the corridors of our hotel. I don't know what is that context is this one, but we can now create, and suppose this is a graph we have, and these are actually, so these are edges are actually what? Corridors, and the intersection point or end points are actually vertices. So these are the vertices we have, and these are the corridors. So these are the rooms besides you can think. Okay, these are the intersection point is actually these nodes are actually intersection point of corridors. Okay, this is we have the graph. Now we want to cover the what is the vertex cover. First we will try to cover the edges. We will choose such edges, okay, so that the maximum number of vertices could be covered. Like, so how we can choose, or not even the what is the vertex cover? Minimum vertex cover is different. First thing, what is the vertex cover? What is the definition of vertex cover? Anyone is there that can tell?
It's a point or it's an edge where it's a vertex where you can have a view to multiple edges or maximum edges.
Yes. From there, we can see. So, can you tell me what is going to the vertex cover? It would be a subset of, if all of you gone through with the definition. If anyone is gone through with the definition, so what is going to be? Vertex cover is going to be subset of vertices or edges. So edges is, suppose V is collection of vertices, okay, all vertices, and E is collection of edges. So this vertex cover, I'm not saying minimum vertex cover, I'm just saying vertex cover is going to be subset of edge or subset of vertices, that V.
Subset of vertices.
It is going to be subset of vertices. We'll try to cover, we'll choose such vertices, or we'll choose vertices so that it will try to cover the edges. So now if you choose this vertex, it will cover this edge. If you will choose this edge, this will choose this edge. If you will choose this vertex, It will cover this edge, this edge, this edge, and this edge. 4 edges it will cover. So how we can choose minimum vertex so that it will cover maximum number of edges? How we will choose minimum number of vertices so that it will be choose maximum number of edges? That is called the minimum vertex cover. We'll try to cover the edges with by choosing the minimum number of vertices. So suppose, for example, if you choose B5, okay, if you will choose B5, then this is done, this is done, okay, this one is done, this one is done. So 4 edges is done. Now if you choose B2 or B3, then it will only cover this one. But if you choose B1, then it will cover this one and this one also. So what we are trying to do, we will try to choose the minimum number of vertices, which will cover the maximum number of edges. Okay, just a minute. Okay, so we'll try to choose minimum number of vertices so that it will cover the maximum number of edges. So that is the meaning of minimum vertex cover. Okay, so now if we chooses V1, now what we can choose so that maximum number of edges would be done. If we choose B4, then this will only cover this one. But if we choose B7, this one, then this will cover, this will cover. Now if you choose this one, then it will cover this one and this one. And almost everything is done. Is there any minimum less than, except 4? If you try to choose with the 3 vertices, is there are such vertices, 3 vertices, so that it will cover the maximum number or even the all edges? Here meaning to say, we'll try to cover or we'll try to choose such vertices, it will cover or it will almost, not even almost, cover the all vertices with whatever you have chosen the vertices. It will cover the all edges. Okay, so if you try to do that, it will be not going to be lesser than with this one. So if you count this cardinality is going to be 4. So the minimum vertex cover, you will say that it is going to be 4.
Sir, but answer is different, right? It's
It
a
could be
B1,
different.
B5, and B8.
So it could be different. So that's why it could be different. Either it could be, it could be chooses with the, different, even B9 or some different number. Either it could be, if you choose B5, then somebody will choose B4 and they will choose B0. So like this, they will try to choose and it will, but the cover, like the cardinality, if you count, it will become as the 4.
So why do we need vertex cover?
So that's why I'm saying, no, that installing the camera. Suppose these are the corridor and we want to put or install the camera so that all corridors will be covered with the minimum number of cameras, right? So that the expenses will be less.
Okay.
This
so
is one way to, yes,
from those places we can cover all the corridors.
all corridors.
So the question 10.2.1, this particular question, which answer is different was said, right? That is because the question that is asked is a bit different. The question that is asked is, you find the vertices where the employees can reach vertices means the vertex covers. At these vertex covers, they are building an emergency room or assembly unit or whatever they call. Okay. So in case of an emergency, if the employees have to come out, what are the minimum points where all the employees can come out without passing to other buildings?
Yes.
Okay. In that sense, it is B5 because from B6, B2, B3, B1, you to B5 you can come. Similarly, it's B1 and B8.
Okay. Yes.
Sir, in a graph, there could be different number of vertex covers.
No, vertex cover is going to be a number, no? So that is always going to be unique. Yeah, that set, this set, whatever I am talking, this set, this could be different.
Okay, means this can't be a unique set. This can be.
This could be, this may not be a unique set, but yeah, that number is going to be always fixed. If it is 4, then
Vertex
however
cover
you
is a
will
number.
count, it is going to be, you want a minimum number of vertex or minimum number of vertices, so it could be always unique. That is, in this case, it is 4.
Okay. So
When will we need maximum vertex covers?
Maximum vertex cover is
Minimum
going
I
to
can
be
understand.
installed on the all vertices then.
No, is there any practical application for it? Because minimum I can understand. For example, you want to, this is a whole building. You want to build multiple buildings are there, B1, B2 to B9. If you want to install some emergency rooms, right?
Yes.
You can have minimal vertex cover. But what is the application of a maximum vertex cover?
So there is no maximum vertex cover. There is another, the definition is there, independent set.
What does it mean?
Independent, what is the independent set? We will try to cover the maximum independent set is there. There is one word, a maximum. So there is no word, you will say the maximum vertex cover. Okay. Always will try to cover with the minimum number of vertices. But there is another concept, maximum independent set. So what is the maximum independent set? So let me take again an example.
So this means there is no maximum vertex cover. Only always minimum.
Yes.
Okay.
Yes. So what is the maximum independent set is? First thing, what is the independent set? What is going to be independent set in a graph? Anyone is here can tell that it is going to be subset of set of all vertices or set of all edges.
No, it's a set of subset of vertices. Okay. It's a subset of
Independent set
vertices.
is not going to be subset of vertices. It is going to be subset of edges.
Okay.
So for a graph, there could be many, like different of set of vertices. Like, what is the definition? That if you choose this edge, okay, if you choose this edge, then you cannot choose this edge. What is that? Why the reason is these two edges are actually connected with one vertex. So you will try to choose such a way, or such, you will try to choose the edges so that two edges are not going to be connected. This is the definition. So like you cannot even choose this one.
So
You can
two
only
edges
choose
must
this.
have a unique set of vertices.
So it is not going to be set of vertices. It is going to be set of
Edges.
subset of edges.
But those edges must have unique vertices.
Those edges is actually not going to share the vertices.
Yes.
You cannot say that, okay, these two, if there is one edge, that means there is, these are actually vertices. So if you are choosing in your set, suppose I am making a set, okay, this is one edge, this is another edge, this is another edge, this is another edge. So edge means that means surely it will be connected with two vertices. That's the meaning of edge. Or if you see the definition, it will be very much clear that what is the definition of edge. Edge means edge is nothing but a straight line, or even it could be a edge is a edge is what? If you see the definition of edge is nothing but a line, you can say, or whatever you curve, or whatever way you can say, that it will actually connect joining two vertices. So if you are talking about one edge, that means surely it will have two vertices. So these are the vertices you have. Then you are saying this is going to be independent set, means so surely it is no two vertices. This one is this one is surely it will all will be different. It is not going to be same. Like if it is V1, then it is going to be V3. Then it is going to be V4. This is V5. This is V6. This is V7. This is V8, V9. But any one of them is not going to be the same. If they are same, that means they are joined. Suppose this is here is V2 and here is V2. That means V2 is going to be here, and what is that? Here is going to be V1 and this is going to be V7. Right? This is 7 here. If these two are connected. So if I suppose I chose B3, okay, I choose V3 and then B7, okay. So surely, sorry, this is going to be not B7. This is going to be edges, no? So this, suppose I am choosing B1 and B3 edge, this edge, and I am choosing this edge, B4 and B7. These two edges are not actually connected with the one vertex. So this is one independent set. This is one independent set. So similarly, if you choose even maximum number of edges, none of them is going to be connected with one vertex. That is going to be the maximum independent set. Even single vertex is also a independent set for the given graph. Like I'm just writing the edge B5, B6. Okay. So this means this is a independent set. Am I audible?
Yes, sir.
Yes,
Yes,
yes.
sir.
Yes, sir. Yes, sir.
Yes, sir.
But we want maximum number of, we'll try to choose, okay, we'll try to choose edges so that maximum number of vertices could be covered. So that's why I'm using the word now covered. The definition, if you see that is how you have to choose such a way that your edges, you have to choose such a way your edges so that even maximum or not maximum, all vertices will be covered. All vertices would be covered. So if let's say now I am choosing, or I am trying to find the maximum independent set, so how we can choose our edges? So can you tell me that how we will choose our edge, or so that all vertices is going to be covered?
Sir, will not you choose the vertices which are covered by most number of edges first?
We'll follow the independent set definition. Maximum independent set is going to be, they are not going to share their vertices. So suppose I am choosing this edge B1, B3. Then I cannot choose this, but I can choose this edge B5, B6. Once I chose B5, this edge, then I cannot choose this edge. I can choose this edge.
D4, B7.
B4, B7.
Then B0, B8.
Now once I choose this one, then I cannot choose this one, but we can choose this edge. So if I will choose this edge, okay, if I will choose, okay, B0, B8. Okay, and then we are done now. Except these sorry, this one, okay, this one, and this one, and this one, except these four. Now if you choose any edge, surely they are going to share their vertices. So this is one independent set. Okay, this is one. Is this maximum independent set? So this is not your maximum independent set, because it is not choosing, you know, B2, B9. These vertices is not actually in this, not choose by these edges. This should be also there. So how we can choose? So this is not maximum independent set. So how we can choose in this situation the maximum independent set? So what is going to be now the edges? Okay, anyone? If we choose, okay, if we choose this one, this edge, and this edge, and this edge, if you choose this edge, this is done, this is done. If you choose this edge, this is done, this is done. If you choose this one, this is done. Okay, so now still there is a issue with this one. Okay, we cannot, anyhow we cannot choose this edge. So we should not to choose this edge. So this one also. If he chooses this one, this is done. So how we can find the maximum independent set? Now, anyone? If you want to cover this vertex, am I audible?
A second.
So if you want to cover this V9, anyhow we have to choose this one. Okay, let's try to do find. So now, so even, you know, if it is not possible to choose all vertices, so that is you can say this is going to be the maximum independent set. If now ahead, if you move ahead, like if you chooses this one, like if you accept those edges, if you choose now another edge, surely they are going to be sharing the vertex. So in that case, that is going to be the maximum independent. So that is one error I said. It is not going to be choose all edges, sorry, all vertices, but it will choose within the constraint. It will try to choose the maximum number of vertices. So surely if you want to cover V9, we have to choose this edge, and then this is done, this is done. Okay, you choose this edge, and if you choose this edge, then this one and this one is done. Now so if we choose this edge, then this one is done. Now this is already have done, so we have to choose this edge. If we choose this edge, then this is done, this is
Sir,
done.
sir, it is not possible to cover all of the vertices in.
Yes, so it is not possible. Here is all vertices. So, but yeah, that's the meaning I'm saying. It is we'll try to choose such a way of all, we'll try to choose where edges such a way that it will choose the maximum number of vertices. Okay, so this is one independent set as this marked 1, 2, 3, 4. If we'll try to maximize more, then can we maximize? Can we add some edge so that it is not going to be cover? Sorry, it will going to be cover more than this vertices. It could be never, I think. Okay, so this is one way to choose that. This is one maximum independent set. Then whatever we have the maximum independent property, that is very similar. We have graph coloring thing. Okay, what is the graph coloring thing? Is that if we cover this vertex with one, suppose this is red color, you colored this vertex with a red color, then you cannot color this edge with the red color. That's the meaning. Coloring of the graph means we'll try to color the only vertices, and there is one constraint that we cannot color this, or we cannot color two vertices if they are connected with one edge. Okay, so we cannot color with this, with the this one is as red. Okay, so we have to choose with different color. So let's choose this is as a blue. So we chooses this one blue, then we cannot choose this is blue, and we cannot choose this one as a blue. So we have to choose with the yellow, surely, or even no red. We can choose with the red, not even yellow, because this is not sharing. These two are not actually joined with the NH. So we can color with this one. B3 is red. Okay. Now this is red, this is red, so we can now color it with the red. So we can color with this one as a red, but we cannot color this as a red, so we can color this with the blue. Now blue and red is then this is not, this is not. We cannot color with the blue and red, but we can color this one as a any one of the blue or red. Suppose I am coloring with this blue. Okay. Okay, this is blue, then this could be, this is surely red, and this is surely blue. Okay, this is the possible thing now, but we have till now we didn't color this. Only two color is till now we have uses and colored are only except two vertices. So is there needed 4 or 3 is also could be done. So if we choose this one with the blue, we can color here.
No, sir.
Yes, we can color
So
blue.
This blue we can color now, but we cannot do this with red. So surely we have to at least needed a different color, which is yellow. And except this, everything is now done. So this is one coloring thing that we will try to color the graph with the minimum number of color. So this is the coloring of the graph. You can say 3 color is suffices to color this whole graph. Coloring means you cannot color the edges, vertices, even the whole page. This means that you are trying to color with the nodes, vertices, minimum number of colors. Okay. Now except these two, now there is some different representation is there with the same graph. We will try to move ahead with the different representation that is called matrix representation, and the list is there, no, that is called list is that is name is that list, the same list name is there or different name is there? I think list is name.
Adjacency list and adjacency matrix.
Yes, adjacency matrix and adjacency list. So matrix, or so what is the adjacency matrix first we will see, then adjacency list we will see. So adjacency matrix is that you will write, we'll try to make a matrix. Matrix, what is the matrix? Matrix is an array. It is an array, okay? And in that array, you will try to fill out with the numbers. Like what is that? Here is how many vertices are there. You will note that this is, suppose this is B1, 0, B1, B2. So like this you will make. This is B3. This is B4. This is B5, B6, B B7, B8, and so how many vertices in this graph have? I just list out in this fashion, and here is again in this fashion B1, B2, B3, B4, B5, B6, B5, B6, B5, B6, B7, B8, B9. Like this, we will list out, or we just noted the all vertices now. Now, how we can write 0 and 1? This matrix, our adjacency matrix, have only the entries 0 and 1. When we will give the entry 0? If there is no edge between two vertices. And if there is one edge between two vertices, then we will give 1. So by this way, we'll go from row wise and column row wise. We'll go and we'll try to cover with the column. Like here is, this means that if I'm drawing this line, that means there is an edge between B0 to B0. So there is no meaning to say. In that case, you will put always 0. So this is for undirected graph. Okay. So for undirected graph or undirected graph, it would be different. Okay. For undirected graph is actually the adjacency matrix is symmetric. Why the symmetric? Symmetric means if you will take the transpose of that matrix, what is the transpose of a matrix? Means whatever the row wise entries written, already you will write with the column wise. That is called transpose of. So we'll see it here. We'll easily see it here. If two vertices which join an edge, we'll give 1, otherwise we'll keep 0. So B0 and B0 is already, it is not, so this is one ambiguous, you can. So in that case, we are not going to, this is the independent, infinite sign is there. The same case is there. If two B0, B0, we are not going to consider. In that case, we will substitute 0. B0 and B1. B0 and B1 is here. They are not actually connected. You will give 0. B2 and B0. So B0 and B2, they are actually not connected. So you will give 0. So by what are the vertices is connected with the B0? B8 and B7. Let's go to the B7 and B8. In these two entry points they are actually connected. Rest R is actually not connected, means in that case you will put 0. Now similarly for B1, B1 is actually connected with B3, B2, B5. Means this is connected with B5, P5, B2 and B3, and rest all is going to be give the entry 0. Likewise, we will do this listing out. We'll do this listing and like this. So finally, what you will get in matrix form means it in standard form. If you want to write, you can write like this, or whatever the notation means. You will like this, and then 1, then 1, then 0, then similarly 0, 0, 1, 1, 0, 1, 0, 0, 0, 0. So like this, if you list out, so this is a matrix, or this is called you can call as it as a adjacency matrix, or this one. But here is the meaning that this is B0, this is B1, this is B2 till B9. And here is again B0, B1 to till B9. Okay. So this is the way listing out this is the one representation of graph that we can convert a graph in the more, theoretical portion. We can convert in the more mathematically. We cannot always draw the graph. We can convert that graph in the some standard form, that is our matrix representation, adjacency matrix and adjacency list. Similarly, adjacency list is there. It is the same way. It is listing like this: B0, B1, B2, B3, B4 till B7. It will be like this. We'll make a table, and in this column we'll write the vertices in the curly bracket that B0 is connected with B8 and B7. So B8 and B7. And if it is B1 is connected with B3, B2 and B5. B2, B3, B5. So like this, whatever B2 is connected with the whatever vertices we'll write in the curly bracket. So this is called the representation of adjacency list. Like this, we are listing out. Okay, is that clear? Am I audible?
Yes, sir.
Yes, sir.
Okay. So this is a way to write that this is a representation of we'll try to convert a graph in the list-wise or in the matrix form. Okay. Now let's move on to the BFS and DFS. So first, we are going to study about the BFS.
One question regarding this adjacency list and adjacency matrix.
Yes.
When we have to use what?
Sorry, when we will use what means 0 and 1?
No. When we have to use adjacency matrix and when we have to use adjacency list. In what circumstances?
So list, actually, these two are actually used in, when you will study Python you will see easily, okay. Even, CT, you are doing the CT course there, you can also see. But in Python, generally, this is just giving representation, that graph could be represented like this. Then there is one concept, matrix multiplication, and there is one concept, transitive closure, and there is an algorithm with the finding shortest path, longest path. This could be done on without going with the, you cannot even always draw the graph of a, for any problem. So what we can do, you can convert this adjacency or the graph in the form of adjacency matrix. Okay, generally we'll talk about the adjacency matrix. List is generally could be not used, but this matrix is always used.
No, for example, if I have been given a graph, okay.
Yes.
So should I solve the problem that is depicted in the graph through adjacency matrix or adjacency list? How do I decide?
So that's why I'm saying there is no, till now you will not see the use of adjacency matrix. Yeah, if it is given, your graph is given in the adjacency matrix, you can convert that adjacency matrix in the graph form, and easily you can deal, because always you cannot think with the how you can think that okay, B1 and B0 is connected. Anyhow, you have to make a rough diagram for that. It is going to be B1 is connected with B2. So like this you can think, or B1 is connected to B2, B2 and B1 is connected with B3. So you convert your problem, the adjacency matrix problem, and convert it the graph and then solve. Okay. This could be done when you will study the week 11. No? So there is one transitive closure. There we'll study the matrix multiplication, and we'll try to find this, this how you will multiply this with the same matrix, and you will find the finally, or you will multiply with the multiple time, and then finally will reach to the graph which is called transitive closure. Okay, how many vertices are there? That time you will, one less than that, you will multiply.
Sir, just imagine the vertices in terms of the cities connecting the air routes. Okay, if this problem has to be solved with respect to what is the shortest distance going from X to Y, If I convert that into a adjacency matrix, right, the amount of
Yes.
space and computation power required is very high, right?
Yes, yes.
So adjacency list is better, right?
So, but how you perform? There is no better algorithm to perform your work on the adjacency list. But for the adjacency matrix, there is already matrix multiplication is there. So generally there is no use. This is one kind of listing out, or if you have given the list form, you can draw the graph. But this is one beautiful use you will see in the next week.
Okay.
Now let's move on to the BFS. What is the BFS means? Breadth first search. Okay, and what is that? This algorithm. This algorithm is very simple. This is one kind of, this algorithm. This is one algorithm. Okay, this, what is the use of this algorithm? The use of this algorithm is, it will try to, suppose your graph problem is very big and you don't know where is the is that graph is connected or not. So one example I am saying that VFS will do that. Even that VFS is also try to find a path between two vertices, and it will give the, is there any path between two vertices or not. Okay, they are connected or not. So BFS is algorithm is used. There are many use, but these two use we can see. Okay, that graph is connected or not. So for that to start BFS, this is a use. You want to check that is this graph. Suppose I'm just adding extra
Sir, the
vertex.
BFS is the same BFS like what we learn in DSA?
DSA. What is the DSA?
Data structures and algorithms.
I think so. Yes. Suppose I'm just adding one vertex. So what we can do, if you BFS needed a starting point, suppose I'm choosing a starting point vertex B1, and you will do the algorithm, BFS algorithm will see, and it will slowly reach to all vertex, and also it will reach to B10. And by this way, you cannot go from here to directly here. So it will give that, okay, you will get two component, or two, that graph is not connected in the different word you will say. Okay, so BFS is generally the graph is connected or not, or other applications are there. Till this time I am not getting that, but yeah, simply is that generally searching to that, is that graph is connected or not. There are other applications are also there. So what is the BFS? BFS is needed, starting point. Either it could be any one of the, you can choose. Okay, this is one general, either it could be asked in the problem that they start the BFS with the particular vertex, or I'm saying for the general case, I'm assuming that it is started the algorithm from the vertex V2. Okay, sorry, B2. Now what is that algorithm? Algorithm is, will that, Q or other things we'll see later. Okay, what is that in the graph wise, let's see first, then it will be very easy to understand with the making with the Q. Okay, what is the Q and what is the label, will easily see. Okay, once first let's do on the graph. Okay, so what is the BFS that, okay, in the BFS that, it's in the problem said that start the BFS algorithm. This is one algorithm. Okay, what is that algorithm? That algorithm is to search or to reach the all vertices. Okay, I want to start from the vertex B2 and try to reach all vertices. Okay, so I started from B2 starting point, let's go to B1. Okay, and from B2, is there any other vertex where we can go? So that is called visit. From B2 I can visit only B1. Okay, from V2 I can only visit B1, I cannot visit other vertices. Okay, once I visit, okay, I will try to explore. So I can only explore B1 now. Explore means I will reach to B1, and from B1 I will start looking other vertices. That is called exploring. Okay. So I started from B2 and I able to visit only B1. There is no other vertex I can visit. So and now I reach to B1 and start visiting again. So that is called start visiting from B1 means started exploring B1. So I started from B1, I started visiting. So I can visit this V3 and I can visit V4. So what is I am actually writing here? So from B2, I reaches to V1 first. This is one. So I just, this is one level. If you want to give here is level, I just, the first place is there. I can visit from V2 to V1, only V1. So I just given this vertex as a level V1, sorry, 1, level 1. And from B1, I can visit, means I can see, I can keep a, telescope and I can see two, planet that which is B3 and B5. So that means I can visit V3 planet and V5. Then I just give, I am just giving, this is 1, and then I just added 1 plus 1 added here. So this is 2 vertices I can visit, means I just given level 2. Okay. Now I will only visit it. I took the telescope, okay, and I visited a planet which is V3 and V5. Start exploring means I will go to V. Okay, now I will go to V3, sorry, B3. Start exploring B3. Okay, start exploring B3 means when I started V3 exploring V3, I cannot visit any other vertex except B1, which is already explored. I already have seen, visited and explored. Except B1, I cannot see other. So I will back to, okay, here. No, I will back to the same B1. Now I will go to the same level. This is already 2 levels. So, and already this one is same level B2. So now I will reach to Hen and start explore. So from B5, I can see B1, which is already done. So we are not interested in that. We can visit from B5. I can visit planet here, B6. I can visit this one. I can visit this one. So what is going to be level, or I want to give the numbers. What is going to be level in that case? Anyone?
So for all the 3, we can give 3 only. Like
all 3 we can give 3 only, because from 2 I can visit these all. So this is going to be 3, this is going to be 3, this is going to be 3. This is the leveling. We'll see the leveling. What is the use of leveling? There are some activity problem, otherwise there is no use of that giving the label. Okay, there is, I will tell you the use also, different use. Okay, either you can see on the solvitus what is the use of this level. Solvitus have the main, you can, some problem is there, you can use, see that what is the use of level. We'll see later while discussing some activity or practice. So this is the level 3 I just given. Means from why it is 3 means from B2 I can see V6 and V4 and V7. Okay. From these 3 means from V4, V7, V6, anyone I can go. I can go directly to B4 and start exploring. Either I can go B7 and start exploring. So I'm just going B4 first. Okay, I just going B4. So from V4, I am just started visiting. It is already visited by B2. It is, and B2 is already visited. So there is no use. So we can, okay, we can back to the B5. Okay, and from V5 I can again go on to V3, B7. With the same level I will go. Okay, we cannot go with the different level. I can go B7. So B7, okay, I can visit B5, but also I can visit B0. So what is going to be the level for B0? It is going to be added here plus 1. That means 3 plus 1, which is 4. Okay. And I can visit it now, but till now I didn't explore. Okay. Now the term for exploring, what, okay, it is done. Visiting is done. Now I want to explore. Okay. So and already B7 is, I explored that. From B7 I explored B0. Now I will go to which, so this is now preference will given that first come and first out, that okay. So which now I want to explore that which vertex I will explore. I will explore B naught or some other vertex, or do anyone have remember that which vertex I will start exploring now once I explore B7? Anyone? So see that's why the label use. Like now see that this is level 3, this is level 3, this is already done, this is a just now we did. Here is one remain, level 3. So we will explore first this one, then explore this one. We cannot go this one. This is, that's why if you see that's the use of Q. Now we'll see how it could be. In the same, I'm just reading out with on the graph. Okay. So until now it didn't made tree also. So let me list out that here in the form of tree. BFS give a tree. Okay, how it is that I started from B2, so I just given B2. From B2 I just reached to here first B1. Okay, and from B1 I visited B2 and B3. Okay, so after this one, so I just go to B3, okay, and explore, and also again back to here, and then I visited this B5 and then explored. And from B5 I visited B6, B3 and B7. So from B5 I visited B6 and explore, I visited B4 and explore, and here is B7. These 3 vertices I visited and explore. And now from, so I just given preferences. Now I will start exploring from B0. So from B7 I start explore that B4 is here. Okay, no other vertex. Okay, so now B4 is there. From B4 I started exploring the which is already this one. If you will see this side, it is already explored. So we'll go to this one. So from V4 I will visit V8, and once I visited I start exploring V8. Okay, so this is V8, and again from V8 we can only see V9. Okay, okay, and then from V9 I can explore that. From V9 I cannot go from new vertex, so start backing, means from V9.
No,
and
from
then
B4 to B8, how are we exploring that?
B4 to B8.
Yeah.
So B4, here is we are. So I visited, I can visit from V4, V7 and V8, but V7 is already, visited and explored. So I will need to go the new unknown vertex, which is already B8.
No, that
Which
is
is
B0, right? From
B.
B7 to
B8,
B0,
no?
right?
From B0 to B8. This is 8, not 0. This is 8. And this is 0, B0.
So directly connected edge is not necessary for visiting that vertex, right?
No, directly connected edges is actually used for the visiting vertex, no?
No, sorry, in the diagram what you have written, no? B7, B4, B8, B9 you have written.
Mm-hmm.
So after B7, you visit B4.
Yes.
Okay.
Huh.
From B4 to B8, there is no direct connection, right?
B4 to B8.
That
Where
is
is
what you have written.
B4?
The
B4
diagram.
is, there is no nothing. From V4 there is no.
No, you have written in the diagram.
B4
The new
and
diagram what you are drawing, no? There you have written B4 to B8.
B4 to B8. There is no B4 to B8. From B4 I just back to B5 and then explore B7. There is no direct edge. There is no, these two are not connected. From V4 I didn't able to explore, no, visit. From
No.
V4
not on the right side. You go still on the right side. Not I'm not talking about the diagram where B5 is there. You come from B5, you come to B7. B7, you go to B4. Okay. B4 to B8. You're writing as B8, correct?
B4. So this is 7. This is 4. From 4 B7 to B4. So I wrote here B4. Oh. So here is 0. B0. Sorry.
Okay.
Sorry. This is B0. I just wrongly wrote here. This is 0. This is level 4. Because of level 4, I just wrote 4.
Okay.
So this is algorithm. This is the algorithm. Visiting and then explore. So what is this in the queue-wise? Queue-wise, we can, queue-wise, what is that in the queue-wise? The same way, we just whatever just read out, no, we'll list out in the queue. So what I did,
B9 is at level 4 or level 5?
So this is going to be 4, and then from 4 this is 5, and this 5, and then B6. Sorry, so this is level 6. B9 is going to be level 6.
Okay.
And this is going this is our BFS tree. Okay, let's do on the queue wise, then it will be more clear. So what is that again? We started from B2. Okay, so let's make it the queue. So I started from B2. Okay, I started from B2. I can visit B1. Okay, only visit B1. So I just list out that here B1 and no other vertex. So here is not B1. Here is, it will be like this. From I started from B2. I can visit B1. Okay, whatever. So this, so there is something name is there, that what is that name is label. This is one. What is that? I have to see that once again. Just a minute. In the list wise, how sir is doing that, I just want to see. So there is no there's no head thing. There is no use of this one. This is the queue we have. Okay, so for I started from B2, I can visit B1. So I just list out B1 is here. Okay, and now I started exploring. So once I started exploring, okay, B1. So that means started exploring means you will erase B1. From B1, I can visit B3 and B5. Okay, B3 and B5. Okay, now once I did this, then start exploring B3. Suppose I am exploring first, because I just list out in the order of in increasing order. You can give here 5 and then V3, whatever, because from V1 I just visited, both have the equivalent priority. So either whatever the way you can choose, I just suggest with the increasing order of numbers. So V3. So from V3 I cannot visit. Now once I started exploring V3, I just erased this B1. Okay, and it will be shifted here B5. This means that this is remain to explore. Okay, I started exploring B3. There is no new vertex which I visited from V3. Okay. Okay. Then I5 started B5. Once I started exploring B5, I will erase that. And from V5, I can see B6, I can see B4, I can see B7. And I just list out those all, which I can see from these are the visiting, means I just list out the visiting. Okay. Now I started exploring. So B6 is there. I just list out in that fashion, whatever the order you want, you can all have the equivalent property. Okay. So B6 now started exploring means I will erase B4. Okay. So now it will shifted to B7 and B4 and B7. Exploring, once I started exploring, there is no new vertex. This is done, and back to here B5. There is no back to is for work for DFS. Okay. This is done. Now B4 is remain. So either B7 we can go. We cannot directly go in this order I just wrote, so I will follow the order. So I just go B4. From B4, there is no new vertex which you are looking at. I just erase that. Now B7 will be shifted here. The same way. Now from V7, there is no new vertex. There is one new vertex B7. I started exploring means I will erase that. Now I will list out that. What are the vertices I can visit from V7? So V0 only. So exploration of B7 is done. From B0 now we'll come to V0. From V0 only I can see B8. So I will just reach to, or I can visit, and then once I started exploring B8, I can visit V9. So V8 is be done and V9 will be written here. Okay. Now there is no other vertex. So B9 is now I started exploring, you will erase that. That means started exploring means you will erase that. Now there is no new edge. We are done, and our queue is also empty. Okay. Is this clear? A bit clear or something? I don't know. I don't know. I am able to explain that BFS algorithm or not. No, yes, no, anything?
Yes, it's clear.
Yes, sir, it's clear.
It's clear.
It's clear, sir.
And what is the same way? What is the DFS? So this I made, no, this is the level that's why I made. This is level. We got this is called BFS tree. Tree, will see. Tree is what? Tree is nothing but a graph which don't have any cycle. In this graph, you can say it not contains cycle, means you can not find an edge between two vertices which will form a like this triangle or any circle or any, it's not circle, it is any kind of, you cannot find a loop kind of thing. In such situation, that graph is called tree. So this is a BFS tree. DFS is also very easy. DFS is nothing but surfing on the exactly on internet. DFS is what? Exactly on internet. What is that? Okay, what is that? You are on the Google Chrome page, this page. Okay, you typed here something. Okay, and it will give the some list of links. Okay, and what you will go here and start clicking on. You will click on this link and go in. And once you click on this one, some link is given here. Okay, some link is already given here. So we'll choose one link, any one of the link. Either you can go directly, any one of the link you will choose. And once you choose this link, okay, and we'll go to link, or even let's say one link. One page is there. Sorry, one page on reach to on this page, and you will go this page. And from this page, this is, you can say, PDF. You got a PDF, and there is no link in that PDF. So you will back to here. What is that? You will back to here and go to the another page, and you will just click on. You will reach again. There is no page. Back to here. Each time you are getting the PDF, and this is done. This all are erased now. So this exploration is done. Now you will back to your list out here, but you whatever you want to find that page, you didn't till now you didn't find, so you will back to here, list of the links, and what you will get, you will go to the another list and go inside that, and inside that you will go in if there is, you are able to find, yes, if not, then back to here and then back to here, then go to the another list, go to in, go to in, go to in, if you found that, then done, otherwise back to the same. Are you all of you are getting that? This is exactly DFS. Whatever you know in the searching on the internet is exactly on Chrome, whatever you will do. This is the DFS. Exactly, this is DFS.
Sir, so in DFS and BFS, the main difference is the order in which we are checking the notes.
Yes, it is actually what this is in the DFS, you know, on the V2 it will be very clear. On V2, what is the difference? That I just started exploring B4. Once I did, then I go to B7 on the same level. Once I did, then from B7 I able to see B0, but till now I didn't go. First I finish this one. Once I finish this one on the same level, then I go to V4, that sorry, B0 of the new that level, next level. Not go directly without finishing the same level, you cannot go to the next level. Once you finish that level, then you will go to the next level. But in the DFS, what is that? In the DFS, if you are B2 is here, and suppose I started exploring B4, and then from B4 I will go B7. I will got new route, right? No, so I will go B7, and from B7 I got new route at B0. So whatever I got new route, I will go in. Okay, here is that, here is that. This is the ending point. Then I start backing now. Start backing now. So once I backed here, there is no, it is already visited. So start back here, then back here. And from here, I got, this is the new page, then we'll go here. And there is no, again, there is no ahead vertex, so then again back here. So you will see with the difference here, BFS and DFS tree are actually different. Okay, here we can see the same way. Okay, where is that? Okay, we can see it again. Okay, from B2 I started the same as in BFS, DFS. Okay, I just go to B1. So I'm just writing. Okay, from B2 I just go B1. Okay, from B1, okay, any one of them I can go. Either I can go B3 or I can go B5. Okay, okay, suppose I reach to B5. Okay, so I reach to B5. I reach to B5 here. Okay, then B5, from B5 I can go B6, any one of them. So I just went to B6. Okay, and B6 is in now. Then I will back to here. Okay, I will back, and then these are already from this. These are the visiting I can visit. So I will now go to B4. Okay, from B4 I can visit new vertex, which is B7. Okay, I can visit B7. From B7 I can visit new vertex B0, because V5 is already, we can go B5, but it is already done. So but new vertex, I just got new vertex, I go in, and from B0 new vertex is B8, and then B9, and then B9 is in back, and then from B7, okay, it is already done, then back, and then back. Okay, till now see that this B3 is not done. Okay, so we cannot see, we are not jumping here. Okay, we are till now we are not jumping. I will go to B1, B2 starting point. From B5, then already B6 is back there, then B1, and again from B1, see that our B2 B3 is remain. Now from here I will go to this new B3, and this is now, there is no new vertex you got, then back here, and then from here there is no new vertex, then back here B2. This is the ending now. Now see the differences in the, you know, see the vertex in the tree form. See that it is in the leaf form, it is given. This is This edge is here, but there is no edge here. This is the difference. This is the use of level, and there is no, this is, pre-post number is there. So we'll see later, but this is the difference. So this is DFS tree. DFS is exactly searching on internet, nothing more. Okay, that's all. BFS and DFS, we'll see later more on that. So is DFS is clear? I think it is clear. There is nothing much exactly on internet as you used to do on internet. Nothing more. We'll make a queue in the DFS also, some queue and some list is there. We'll see later that. But this is the algorithm. This is the algorithm on the graph. Is this clear now? Please let me know. DFS is still have doubt?
No, sir.
It's clear.
No, sir, it's clear.
It's clear, sir.
Okay. Now let me know your doubt. Okay. If you have doubt, please let me know. If any activity practice, okay. The topological sorting we'll see in the next session.
Can we go to 10.4? Third question.
10.4. Which question?
It's third question. Oh. 10.4.
This is 10.4.
One minute, sir. Sorry, 10.2. Second question.
This one.
Yeah. So here in the second question, sir, the way how do we find this is just by trying to map it as a diagram or something and then finding it, is it? Or is there any other better method of doing it?
No, only the classing time is there, then you will find an edge.
Or it's just manually we have to find it out, right?
Yes, manually I have to do. Nothing, there is no different method.
Okay.
Okay.
Sir,
That's all for today's session. Yeah, Tanvantari. Yes.
yeah, but how we can manually it's let's say 10 a.m. and 11 a.m. we can form a one edge, and 10:30 to 11:30 we can form a one edge. How we can do that? Since I'm a
No,
little bit
this is now
confused.
meant to say 10:30 to 11:30 there is an edge. What are the vertices you have? Fortnite, Dota,
Yeah.
okay, Rocket League. These are
Rocket
your
League.
vertices.
Yes.
These are your vertices. And if it is the time classing is there. See that this is 10:30 to 11:30. And see that 11:35 is there already. So see that there is a classing of time, no? Racket is 10:30 to 10:40 to 11:40. But Destiny is started already from 11:35. See that Rocket and Destiny have some classing time, right? It is 1 hour, but Destiny started earlier, before 5 minutes. Before
Yes.
ending to the Rocket League, it is started earlier, 5 minutes earlier. Then you can Rocket and Destiny have some edge. So age is going to be what? So age is going to be a classing of time. So Destiny and Rocket League is have an age. Now see that 11:50 is started and 12:50 PM is Destiny ending. That means Destiny and Battlefield have an age. They have the classing time. Similarly, 11:50 is there. So all are actually here before they are independent. Now Titanfall is there, and then so it is started from this to have the classing time. Battlefield and Titanfall, because it ending at 12:35, but Titanfall is started earlier, 5 minutes earlier. And then Hearthstone is there. Hearthstone is also 10 Titan, and these two have. I also Hearthstone have some battle, because Battlefield ending at 12:35, but it is Hearthstone are starting even 12 to 20. So these have age. So by this, whenever they have the classing time, you can find an age. Okay. By
Can
this
you
way, you can
tell about the degree also? I think it was missed.
degree.
Yeah.
So after, yes, so degree is what? Degree is number of connecting edges with the vertex. Like for this vertex, degree is 1, 2, 3, 4. So degree of B5 is 4. How many edges are connected? That is going to be the number of edges connected with one vertex is called degree of that vertex.
So if it is an undirected graph, whether we have to consider outgoing edges or incoming edges as a degree?
So if it is directed graph, then there is one term that in degree and out degree. So if it is directed graph like this, so this is one incoming edge for this vertex B5. So maybe it will writing like incoming edge or incoming degree, no? Sorry, in degree and out degree is there. In degree and out degree. So in degree, suppose and rest all are going to be out. So degree of in degree of B5 is what? 1. But out degree is 4. No, sorry, 3. Okay, is this clear?
Yeah.
Okay.
Okay, sir. We will take up the 10.3.3 in the next session.
Yes.
That is one doubt where I have.
Well, next session we'll see. Okay. Okay. Thank you so much. We'll see in the next session. Probably I will take.
Thank you, sir. Good night, sir.
Okay.
Thank you so much.
Yeah.
Thank you, sir.
Thank you so
Thank
much.
you, sir. Bye, sir.
Thank you,
Good
sir.
night to all of you.
Thank you,
Yes.
sir. Bye, sir.
Bye.